Hello. Today you are to be watching this video. This is the only thing you need to do today is to watch this video and then take some notes as we watch. So this is going to be the start of our very last unit of the semester. And we want to do well on this unit. So this first page of notes that you're taking is really going to be the big pile of notes, the big amount of notes that we need to take. So when we come back after break, we will still have a few notes to take, but this is the big bulk of it. So if you remember the force unit, we had the 4 forces that we used over and over again, and we had to refer back to those to double check, okay, what kind of force is this? This is what we're going to do today, plus do an example of how to show energy transformation. So our goal for today is to learn what energy is, to get 4 main types of force down and when those exist. And then we're going to learn how to show energy changes in a system using pie charts. So it's something that most kids pick up on okay, or at least easier than maybe some of the stuff we have been doing, because pie charts are a type of graph that you've made for a long time. So first of all, what is energy? Energy, if you look it up in the internet, is the ability to do work. That doesn't help us a whole lot because we don't know what work is yet. In physics, to do work means that you apply a force over a distance. So like when you push a box across the floor, you're doing work on that box. Or if you lift something up off the floor, you're applying a force over a distance and lifting it, you're doing work. Another simpler definition, or it's not really a definition, but a way to think of energy is the ability to cause pain. So if an object has energy, that energy could cause you pain. So when I go through the 4 types of energy, I'm going to kind of go back to that definition of the ability to cause pain as we think about how or what factors might affect that type of energy. And then the other thing you want to keep in mind is that energy exists in a variety of forms. They can be changed from one type into another. But what we always want to make sure we know is that the energy, the total amount of energy, always stays the same. That means that energy is a conserved quantity. The total amount of energy that we have in a system always stays the same. We can add energy in from outside the system. We can have energy leave the system, and we'll kind of talk about this as we go through the unit, but our total amount of energy always stays the same. So total energy always stays the same. I should have said this at the beginning. If you do not have a piece of note paper handy, pause the video and go grab one if you haven't already. You want to have this stuff down. Okay, I'm assuming you have your paper ready. I'm assuming you've got what we've written down so far. So now we'll move on and talk about the 4 kinds of energy we need to have for this unit. So at this point, we're going to go through the 4 kinds of energy that we need to have for about 95% of the problems we do in this class. Just like with forces, there will be some forces that we get that don't necessarily fit one of these 4. But this will get us through most of them. So if you need to pause the video, you might want to copy this chart down as we go. We need a column for type of energy, a symbol, the equation. We'll have equations for 3 of the 4 I give you. I'm not going to fill that out today, but leave a spot for it. And when we come back after break, as we get those introduced, we'll add that in. And then a bigger section at the end to write some notes about it. So how to define those types of energies and what factors affect them. So the first kind of energy, most kids will tell me if I ask for volunteers to what kind of energy do you know? Most kids, the first thing I hear is kinetic energy. And this is energy that is stored in objects that are moving. We have a symbol for all of these types of energy. Just like with forces, we always use the symbol F for a force. So for energy, we will always use E, and then we use a subscript down below to say what kind of energy. So EK will be kinetic energy. And the equation column, we're going to leave blank until we get further along. And then going back to that definition where energy is the ability to cause pain, in class, I'll take a ball and I'll say, okay, what if I threw this ball at you? What factors would affect how hard or how much pain you felt from the ball? And so the size of the ball, so I might take like a softball and pretend I'm going to throw it at a student, and then compare that to the amount of pain they might feel if I threw a ping pong ball at them, which is lighter. And so students will then discover or decide that mass might affect the amount of kinetic energy that something has. So the more mass something is, the heavier it is, the more kinetic energy it has. And then they'll tell me, well, how fast can you throw the ball? So the faster I throw the ball, the harder or the more that would hurt. So the speed also affects the amount of kinetic energy. The faster something goes, the more kinetic energy. Notice I'm using speed here, not velocity. The direction doesn't matter. An object's going to hurt you just as much if it's going to the left or going to the right. The direction does not matter for energy. Energy is not a vector. It does not have a direction to it. The other kinds of energy that kids tell me is often they'll say, well, there's potential energy. We are not going to use the term potential energy. Potential energy is actually a type of energy that encompasses many types of energy. There's two kinds of potential energy that we will use in this class. One is gravitational potential energy. This is the one that most kids will think of when they think of potential energy. So we will use EG for gravitational potential energy. If you tell me when we're back in school that it has potential energy, my follow-up question will always be, well, what kind of potential energy? The other kind of potential energy we will use is elastic potential energy. And that will be EEL. We will again get equations for both of these when we come back. But gravitational potential energy is the energy that is stored in objects that are at some height above, we'll say, the ground. That's some. And I'm putting that in quotes because you can define h for the height to be 0 wherever you want. So it's just some reference point. We'll say or reference point. And the amount of gravitational potential energy, if I go back to like pain and using different sizes of balls, if I was to drop a ping pong ball on you versus a softball on you, the ping pong ball would hurt less because it's lighter. So mass also affects gravitational potential energy. So the lighter or heavier objects have more potential energy, or gravitational potential energy. See, I even do it too. And then how high they are. So the higher they are, I spelled high wrong. The more gravitational energy they have. So if I drop a baseball on you from a few feet, that might hurt, but if I dropped it from a few meters, that would hurt more. The higher you are, or the higher the object is when it's dropped on your head, the more it's going to hurt. So therefore it would have more potential or gravitational potential energy stored in it. And then elastic potential energy is energy stored in objects that are stretched or compressed. And then you kind of have to add something to this. You can stretch and compress lots of things. that don't necessarily store potential or elastic potential energy, they have to want to go back to their original position. So they have to be able to go back to their original position or shape, maybe is a better return to original shape. So if I take a ball of Play-Doh and I push it down, I might be pressing it or compressing it, but it's not going to go back to its original shape. But if I take a spring or a rubber band and stretch it or compress it, that spring or rubber band then wants to go back to its original shape. And so that would store elastic energy into it. And this depends on how far it's stretched. So the further you stretch a rubber band, the more elastic potential energy it stores. And then like just how stretchy it is. Some rubber bands are like thicker, they store more energy. So there's a term for that, but we don't need to worry about it right now. It's just how we can just say how stretchy it is, maybe. Just trying to keep it simple without throwing too much complicated vocabulary at you right now. And then the fourth type of energy is one that's a little harder to define. It's thermal energy. A really easy definition for this would be heat. That's not actually 100% correct, but for the level we are at, that will work. It technically is the energy that's stored in the little microscopic particles that make things up. So all matter is made up of atoms and molecules. And when objects get warmer, those atoms or molecules start to vibrate and move faster. And that random motion of the particles that are in the matter is where that thermal energy is stored. So what we will get thermal energy is when we have friction, for the most part. This is where it comes in physics, is when there's friction, so moving things, rubbing together, will warm things up because of friction, and that we will use that energy that gets created because of friction we will call thermal energy. So make sure you have all four of these down. Pause if you need to finish or catch up, and then move on. So the last thing we need to be able to do today is to make pie charts. You will have a practice assignment doing this for tomorrow. I'm going to have this open as soon as you're done watching the video. So if you want to start working on it today, you can, but technically this is your assignment for tomorrow. If you have time today, you might want to do it early right after you're done watching the video so that this is still fresh in your mind, but you could always go back and rewatch the video if you needed to. So pie charts are a way of showing energy. A pie chart, if you remember, represents the whole thing, and then you divide the pie chart into fractions to show how much of each kind of energy it has. So we will show conservation of energy, that the total amount of energy has to stay the same by making our circles, our pie charts, the same size every time. We will divide each pie chart up into the four kinds of energy if it has that type of energy and how much of it proportionally is that much. This is more of a qualitative way of showing energy. We don't care so much about exactly how big each pie section is, just is the kinetic energy increasing or decreasing? Is the gravitational energy increasing or decreasing? And relatively, how much of each there is. So is there more gravitational energy at a certain spot, or is there more kinetic energy at a certain spot? Some things you might want to think about are these three questions here. Where's the energy coming from? So where did it get this kind of energy? What is the energy doing? What does it cause the object to do, or what does it do to its surroundings? And where does the energy go? So what, if it's kinetic energy, it has to go somewhere because our total amount of energy has to stay the same. So if it doesn't have kinetic energy anymore, for example, well, where did it go? What kind of energy did it become? So the first example I'm going to use is a wind-up toy. I'm not sure if I'm hoping you've all seen these kind of toys, the type of toy where it has a little knob. You turn it and then set it down on the ground and it starts to move. So this might be a wind-up bunny that's all wound up and it's moving across the table at level ground. When you make pie charts, one of the first things you might want to do is define where your height equals 0. So your starting height can be wherever you want it to be. Since this object isn't changing height at all, the easiest thing to do is say that where these bunnies are is where your height equals 0, because then we aren't going to have no gravitational energy for the whole time. There won't be any gravitational energy. This arrows on here for each position, that represents the velocity of the toy, and it tells us that it's speeding up. So the wind-up toy is getting faster each time. So since I know it's getting faster each time, I know I'm going to have kinetic energy in each one of the pie charts, not e.g. ek. So in every single one of these, I have to have kinetic energy. And because it's getting faster each time, that kinetic energy has to be increasing. The toy is wound up, so that means there's going to be some elastic energy in here, at least in the first several. And then I can start. So in my first pie chart, it does have it moving, but that arrow is relatively small. So I'm going to make a small section. I'm going to call that EK for kinetic energy. So a small amount of the pie, or the total amount of energy, is kinetic energy. And then the rest, since there is not going to be any gravitational on any one of these pie charts, the rest is going to be elastic. Then, as it goes on to the next position, that arrow has gotten longer, so my kinetic energy is going to get bigger. So I'll make that kinetic energy pie chart a little bigger. And then you might want to say, well, most of the other energy should all be elastic energy, and most of it will be. But eventually, this wind-up toy is going to stop. There's friction as this toy is moving across the table and the gears and other things. So to show the heat that gets created from friction, I'll make a small section of the pie that's going to be thermal energy. Now, when I make my thermal energy pie chart, I'm labeling it an ETH right now, but what I usually do is I color in that whole pie section. I color it in black. And the reason I do that is because thermal energy is very hard to convert back into one of the other forms. It's easy to convert kinetic energy into thermal energy. It's easy to convert kinetic energy into elastic energy. But it's very difficult to take thermal energy and get one of the other 4 types out of it. So I color it in black just so that we're never going to get it back. It's going to, once it turns into thermal energy, it's always going to be thermal energy. The other thing to keep in mind with thermal energy is we never want to include thermal energy in our first pie chart. In our first circle. And the reason is because there's always thermal energy in things. All objects have thermal energy. So we always have it. We just want to show the increase in it. So we're never going to put it in our first pie chart. We're only going to represent increases in thermal energy. So the thermal energy of the system, which is the bunny, is going to increase as the bunny goes across the table. But we're not going to include the starting amount that it had when it began. So then as I go through to my third one now, we can go a little faster because I've done most of my explanations. The bunny's gotten faster, so we're going to increase that kinetic pie chart a little more. The elastic is going to go away as this thing winds down. It's going to get less elastic the entire time because that spring is going to unwind inside the toy. And then the difference then, anything else I have will be the thermal energy. And since it's going to continue to move, my thermal energy pie chart pie section should continue to get bigger. So now the arrow is longer again in my fourth one, so I'm going to make my kinetic energy even more. My thermal energy needs to grow and get even bigger. Oops, color it in. And then my elastic energy is what's going to be remaining. And then when I get to my last pie chart, it's going even faster, so increase my kinetic energy even more. And maybe not quite that much. And then I'm going to make the rest of it thermal. And I will say at this point that the spring is totally unwound. Now, when you do these pie charts, there's a lot of things that we might not know. You could actually include a small amount of elastic energy in here and say that it hasn't completely unwound yet. The exact amount of kinetic energy we have at this point and the exact amount of thermal energy at this point doesn't have to be exactly the same, but I should see that my kinetic energy is getting bigger as I go from chart 1 to chart 2 to chart 3 to chart 4 and chart 5. I should see that my elastic energy is getting smaller and that my thermal energy pie chart is getting bigger. So that's why I added and made that one a little bigger on this last chart when I did it, because I looked about the same as I had here in the fourth one. So I wanted to make it obviously bigger. So that's the first one. Now on these next two, it's still the same toy, but now they're going to be slightly different scenarios. So the toy is wound up and moving along at a constant speed. This is a constant speed, so then I know that my kinetic energy should stay the same the whole time, because it's the same toy, it's got the same mass, and the speed is the same, and those are the two factors that affect the kinetic energy. So I'm going to make half of this kinetic. I'm going to do that on all of them because I know the kinetic energy has to stay the same. And then the rest of this would have to be elastic because I never include thermal energy in my first pie chart. And then as the bunny continues to move, the spring inside the toy will get unwound. And so my elastic energy is going to decrease as I go from the first circle to the last, and my thermal energy will increase. The gravitational energy on all of these is 0 if I assume that this is a height of 0 right here. So I'm going to, as I go into each one, I'll make a thermal energy pie chart section, which I color in black. And then the rest is elastic. And my thermal energy needs to gradually get bigger as the friction is converting kinetic into thermal energy each time. And the elastic pie chart then will get smaller. Oops. I could have just made that elastic, but I like to keep them in the same spot relatively. Here I will say that there's still some elastic energy in it. And then in the third example, height will be 0 here, so there won't be any gravitational energy in any one of these pie charts. We start out moving faster. We have a long arrow here, and then we have a dot here, which indicates it's not moving. Since it's not moving, there's going to be no kinetic energy in this last pie chart. So it's moving here, so I will give it kinetic energy, and it's also going to be wound up probably still, so we'll give it some elastic energy. And then as it moves, my kinetic energy is going to get smaller because my arrow is smaller right here. So that means it has less kinetic energy. That kinetic On this slide, I'm going to go through examples, a pie chart example with friction and without friction. On your homework, sometimes it's very clear that an object should have friction. Other times, it might not be so obvious, and in those cases, you can sometimes ignore the friction. So in the case of a roller coaster on a track, There would definitely be friction in real life, but oftentimes, like in the forces unit, we would choose to ignore it, which simplifies things. So I'm going to do this example on the top as if there was no friction, and then I'll repeat the same thing with friction on the bottom, so you can see how it might look different for two people doing the same problem. So if the roller coaster gets up to the very top, we're going to start it when the roller coaster is at position A at the top. So if it's at the top position at A, that's its beginning position. Roller coasters do move when they're at the top, just not a lot. So I'm going to give it a little bit of kinetic, and then the rest will be gravitational because it's at some height. Nothing's ever stretched or compressed on any of these examples, so I'm not going to have any elastic energy the whole time. And then since I'm going to ignore thermal on these ignore friction, I'm not going to have any thermal on the top example. Then when I get to position B, I'm going to say that the height here where the roller coaster starts out is a height of 0. So when I get to position B, it's at a height of 0. So then I won't have any elastic energy at this position. So this will all be kinetic energy here. When it gets to position C, it's maybe about half the height. So I'm going to make the gravitational energy about half as much, and then the rest will be kinetic, because it'll be moving still at the top. And then position D, the gravitational energy is less than it is at C, because it's not as high. And then this would be, rest would be kinetic. When I add friction into this example, it won't change anything about the first pie chart because we never include friction in the first pie chart. We're going to just have what we start. So that we'll start with gravitational and start with kinetic, mostly gravitational. But then everywhere else along the track, as that roller coaster is rubbing against the track, it's going to be creating heat. So when it gets to position B, it's going to be mostly kinetic because it's going to be going really fast and all of the gravitational will have converted into kinetic. But as the roller coaster moves down the track, the heat that gets created as the wheels move along the track will create a small amount of thermal energy. When we get to position C, our thermal energy will be increasing the whole time, so I'll make that a little bigger. So then it needs to take that energy away from something. It's not going to take it away from the from the gravitational energy, because the gravitational energy is dependent on the height, and the mass and the height of the roller coaster will still be the same, even though there's no friction, or there is friction here and there wasn't in the first one. So it's going to take it away from the kinetic energy section, which makes sense because it's the kinetic energy that, as it rubs against and is moving, that's getting where the thermal energy is coming from. And then when we get to D, likewise, the gravitational energy pie chart needs to stay about the same size. So to account for that extra thermal energy that's there, that's just going to take it from the kinetic energy. So the roller coaster won't be moving as fast when it gets to D because of the friction, as it would as if there wasn't any friction in A. So if there's friction, generally what we see is the kinetic sections are getting smaller, and that the gravitational often will be the same. Sometimes, like if it's a bouncing ball, like for example, it won't bounce as high each time because of the loss of thermal energy. So for tomorrow, your assignment is going to be a practice assignment making these pie charts. It will be open today if you want to start working on it. You could do it all today and have nothing to do tomorrow. It's a Google Slide document. You have the opportunity, you can have the option to either do it on paper, which would probably be easier to just draw the pie charts on paper, or you can use the drawing tools in the Google Slides to create the pie charts. If you do decide to do it on paper, just do them all on one page or 2 pages and then take a picture of the whole page at once and upload one page onto the Google Slide to submit. Or you could choose to just upload an image of your paper and not put it on the Google Slide if you can get it all onto one thing. So you either do it in Google with the drawing tools or do it on paper and upload an image either onto the Google Slide or upload the image into Canvas to turn it in. But that's your assignment for tomorrow. You'd just be creating it earlier if you wanted to.